Okay, we're happy to have Kevin Zhou for his regular seminar at Davis to tell us about G-2.
All right, thanks for the invitation, third time in 3 years. And today I'm going to tell you about something that's very different than the things I've talked about before. It's an honest standard model computation about a very precise effect on the electron G-2, one of the most precise measurements ever made in physics. And it's quite interesting because it is actually fundamentally a one-loop effect, but somehow it's one of those only one-loop effect that has never been figured out before. So another title of this talk would be the world's hardest one-loop diagram and how to do it. So before I start, I want to say this is about electron G-2, and when I tell people about that I'm working on this, the first thing that almost all people ask is, did the mu on G-2 anomaly go away? So this is not about mu on G-2, completely different subject. So the other G-2, mu on G-2, is the one you hear about a lot in the part of physics news. There was an experiment done at Fermi Lab with about 200 people, cost about $100 million. They moved this enormous magnet over, and they flew a lot of muons around the storage ring to measure the spin precession rate and measure the muon G. But the electron G-2 is measured by a much smaller team based in Northwestern and Harvard. The most recent measurement was done a few years ago by a team of 4 people, basically costing just enough, about $1 million, mostly for the fridge. And the way they do it is they only have one electron, because electrons are stable, in a trap that which very, very carefully measures the spin precession of. And that trap is extremely small, whole apparatus fits in a tabletop. Now, the mu on G-2 experiment achieves a sensitivity 1 part in 10 to the 10 for G, while the electron G-2 actually is much more precise. It achieves a 10 to the minus 13 fractional precision. However, you don't hear about the electron G-2 that often in the context of beyond standard model physics, because if you have quote-unquote generic BSM, which means just some generic heavy particle going around in a loop that changes G-2, then the effect is also proportional to the fermion mass squared. And so, because the muon mass is about 100 times more than the electron mass, this is actually, the muon G-2 is generically more sensitive by a factor of 10 to 100 than the electron G-2, even though it's less precise. On the other hand, the electron G-2 is quite interesting because there's a lot of room to scale this up. So right now, the amount of budget and the amount of work in this is very, very minimal. It's been minimal for a long time. There are many axes in which you can make this experiment more powerful by at least an order of magnitude. And also, for the perspective of a theorist, there are completely different theory questions that come up when you try to analyze electron G-2, which are not important for muon G-2 because this is so much more precise. Now, people have been measuring these things for a very long time. So here's a brief history of how we measured all these couplings. When you talk about testing quantum electrodynamics, you actually have to measure 2 different things. Of course, you measure the electromagnetic moment, the thing that gives you the electron G factor, but also to test against the standard model, you need to measure the coupling strength of quantum electrodynamics, which is alpha, e squared over 4 pi, or equivalently the Rydberg constant. Without that, you don't know the thing to put into your loop diagrams in the first place. And so a test standard model has to involve comparing a theory calculation, which starts from Rydberg constant and gives you a calculated electromagnetic moment. And both the precision of these things have been increasing by about an order of magnitude a decade for the past couple decades. Now, for the Rydberg constant, the best way to look for it is by atomic energy levels. So all these searches involve in some way the energy levels of atoms. And the improvement in the past decade or two has been by very, very carefully measuring the energy level differences using the technique of atom interferometry, which basically just keeps track of the quantum phase of these atoms. At the same time, there's been improvement in the electron G-2. So in the beginning, they also did this with atomic spectroscopy. But the electromagnetic moment is a property of a single electron, and it's really best to measure it by just looking at one electron at a time very carefully. And so that's what has been done in the past couple decades. In the 70s, people started trapping electrons, not in atoms, but just in free space. And then in the 80s, they progressed all the way to being able to reliably trap a single electron for a very long time and precisely interrogate its properties. And this was done with a technique called the Penning trap, which I'll explain shortly, which won the 1989 Nobel Prize for enabling this kind of measurements. Since then, people have been incrementally improving it by making better and better quantum measurements, which we are also getting better at doing. Right now, for example, people can move it all the way to the lowest quantum state, measure the quantum state transitions, which tell you about G-2, and there's also potential for quite a bit of improvement in the future. Now, here's the situation today. Now, I told you there's 3 ingredients. We need to know alpha, we need to know the loop calculation that gives you G, and we need to know G. So here are the measurements. The latest measurement of G for the electron is precise at 0.1 parts per trillion, so 10 to the minus 13. It's about a factor of 2 better than the one from last decade. And this is so precise now that in order to compare it against theory, you need to calculate the 5-loop QED diagrams, which has been done by a couple of dedicated groups over the past couple decades. Now, these diagrams look like this, and you'll notice here that there are these 2 different things here for the standard model prediction. there's a white circle and a black circle, and that's because the 5-loop calculations actually don't agree. So there's two groups doing it, they get slightly different answers. Fortunately, it's a subleading problem compared to the other discrepancies. But this is still an open question. Before you ask, it has nothing to do with hadronic corrections. Those are actually much smaller for this context. It has to do with actually evaluating the pure electromagnetic Feynman diagrams. And then you need to compare against the value of alpha from these atom interferometry experiments. It turns out over there's also an outstanding anomaly because depending on which atom you use to do it, you get a different answer. It differs by something like 3 to 5 sigma, depending on how you're counting it. So there is some uncertainty here, but this is just because this is the absolute frontier of what we can measure. Now, if you assume that it's somewhere in the middle, then it seems roughly consistent. Everything seems consistent so far. So if you believe that, then this is the most precise test of quantum field theory that we have.
When you say 0, that's G minus the prediction. That's 0.
Let me see.
There's an alpha over 2 pi is the leading piece, so it's not 0.
This graph has been artificially shifted so that the latest one is just around 0. It's the deviation from the latest measurements.
The top is just
arbitrarily put at 0.
Yeah, just put it 0 to compare how things differ. We're at the level of precision now that alpha over 2 pi is just the first non-zero decimal point, and then all these other ones you gotta put in, and they just I think show some round number here just to make it convenient. So there is still a discrepancy here, though. In theory, you could try to explain this with some kind of BSM physics, but I think it's really that these are just very, very challenging measurements. And this is something that can be resolved in the end of the alpha experiments. Now, let me show you how G minus 2 is measured. And I'll explain why there's actually an outstanding theoretical subtlety here that needed us to address. So the way it's done is you have a single electron trapped in a B field that orbits in a circle and also spin processes at the same time. And these two things are the thing that determine G. The entire thing is placed inside a dilution fridge to make sure it's cool, and various layers of electromagnetic shielding. And then, in order to make sure that it doesn't just drift away in the z direction, there's also an electric field placed in. So this is the so-called quadrupolar electric field, which means that there's positive here, negative here, positive here, negative here. And what that does is it gives you a restoring force in the z direction so that the thing just doesn't leave the fridge. And then finally, you cool the whole thing down to the ground state and look at the quantum energy levels. So here's how it works. There's 2 ladders of energy levels. One quantum number tells you the amount of energy in the cyclotron motion, and the up or down depends on whether the spin is up or down. And so the spin spacing is determined by EB over m times g over 2, because g gives magnetic moment, while the cyclotron spacing is determined by the cyclotron frequency, which is EB over m. And then we can measure the energy levels by just applying an oscillating field and seeing when you can cause transition between these states. Now, if you directly try to measure G by measuring the spin precession frequency, then you have a lot of problems, because we would also need to know E, B, and M extremely precisely. And there's no way of knowing what B field you have in this apparatus to 13 decimal places. So instead, they use a clever trick. And the trick is, in addition, they measure the cyclotron frequency, EB over M, and then the frequency to go from 0 up to 1 down, which is the difference of omega C and omega S. And that difference depends directly on G minus 2. But then when you compute the ratio of these two frequencies, the unknown EB over M just cancels out. And so this is how the measurement is done. They measure these 2 frequencies, omega A and omega C. It's equal to G minus 2 over 2. And then from that, they extract G. The other good thing about this is that this is naturally a very small number, or 10 to the minus 3. So that means your relative precision on G itself is multiplied by 10 to the 3 when you add 2 back on. So this is how it's done. But as you might expect, there are many, many things that can also shift omega C and omega S besides these precision QED corrections. And so everything that affects either of these frequencies at 1 part 10 to the minus 13 needs to be accounted for and subtracted out, which is why this is a challenging theoretical problem. For example, because there is also this quadrupole electric field, there will be some drifting motion up and down, which happens very slowly, and also a motion an electric field that pushes out radially, which changes the frequency of the cyclotron motion. So all these other motions happen at the same time, and they're much, much slower than the cyclotron motion, but they do shift the cyclotron frequency because there's these extra forces in play. You can show that numerically in the current setup, this is part of 1 to the 10 to the 6, so you certainly have to account for this. And the way that they can do this by measuring these other frequencies very precisely and subtracting it out. This is one of those things that you just have to do. Now you can also say, what about relativistic effects? I said that the frequencies were QB over M and G QB over M, and those are just the non-relativistic expressions from freshman physics. But of course, you really have relativistic corrections, but fortunately they're very, very small, because all relativistic corrections are governed by the ratio of kinetic energy to mass energy, which is in this case the cyclotron frequency divided by the electron mass, if you're in the lowest states, and that's numerically by 10 to the minus 9. So there is, the first relativistic correction must be accounted for, and this is there's standard, it's easy to calculate, you just subtract it right out. The second relativistic correction is negligible. Next, you might wonder, what about other QED corrections? And so this is one of those things that's a bit subtle, because in the textbooks we're usually taught, well, to think about QED, the only thing that really happens is you have mass renormalization, it gets absorbed in the mass. Field renormalization, you get absorbed that into, and the only thing that happens at one loop is that G is shifted. But it's really more complicated than that, because in reality there are other things involving, that couple to background magnetic fields. So for example, if you try to calculate the self-energy diagram, then it doesn't just give you a mass renormalization, it also gives you self-energy that depends on the external applied field, which in this setup there certainly has to be one to make the spin precise at all. And so there's a B-dependent part of the self-energy diagram, which needs to be calculated by doing it all with a background field. And then it turns out that the part that actually shifts the cyclotron frequency, but by an incredibly small amount, which is about 10 to the minus 19. So this is actually totally negligible. But you had to worry about it. And then finally, there's another effect, which is not a shift, but is also important, which is that if you have cyclotron motion, so that the particle is going in a little circle, then classically we would expect that motion to damp out because it would emit radiation by the Larmor formula. And at the quantum level that also happens, the state has a finite lifetime governed by the Larmor formula. And when you calculate what that is, you'll find that that lifetime is related to the frequency by 1 part in 10 to the minus 11. So this does not mean that the frequency changes, but it gives an imaginary part. And by the energy time uncertainty principle, this gives you a limit as to how well you can measure this frequency. So that's why this is a problem for experimentalists, is that all of these frequencies you're trying to measure at 1 part in 10 to 13 are actually already brought in at the 10 to the minus 11 level. And so this, a few decades ago, was one of the biggest problems for these kinds of experiments. But fortunately, there is a way to fix this. And so the way we fix that is done in all the future measurements is the entire electron is placed inside a cavity. And then you take advantage of what's called the Purcell effect. So when we have an electron in free space, it can radiate energy by the Larmor formula. But if you're inside a cavity, then the electromagnetic modes are just cavity modes. So they exist at some frequencies, and they simply don't exist at all at other frequencies. And that means that the cavity will backreact and prevent you from emitting radiation in certain frequencies that are between cavity modes. Now, if I just put the cyclotron frequency to be between cavity modes, then that means that I get a nice suppression of the spontaneous decay rate, and this is something that people could already measure all the way back to the 1980s. You could see that this was being reduced by a good amount. However, now that we put a cavity around it, the mode structure of the electromagnetic field changes, which turns out to actually also change the value of XC itself. So now this also gives you an additional shift, and this is the so-called cavity shift that must be subtracted out. Now, the cavity shift comes in classical language from two parts. So if you think about it in classical language or work with Coulomb gauge, you can decompose the electromagnetic field in two parts. One part is the so-called longitudinal part involving these electrostatic Coulomb-like fields, and there this happens because when you have a charge inside a cavity, it induces charges in the walls, and they're like as if there was some image charge outside, on the other side of the wall, and that makes an electrostatic field that acts back on you, which changes the force on you. The other thing that can happen is from the so-called transverse part, which is that because this thing is oscillating, even though the radiation rate is suppressed, there still is some kind of radiation in this cavity, and it will bounce off the walls and come back and act back in the electron, which changes the force on it. So this, at the classical level, is how its cyclotron frequency changes. Now, we can also estimate these also classically. So let's first think about the image charge effect. Well, if I wanted to guess how much this affected the cyclotron frequency, I would just say it's on order of the ratio of the forces from the image and from the ordinary force from the accelerating circle from the magnetic field. And so the image charge force scales as, of course, q squared over 4 pi times the radius of this orbit, so this is just some fiducial radius, r, re, divided by r cubed, where r is the radius of the whole length scale of the entire cavity. And when you plug in the numbers here, you will find that this gives you alpha over m, omega c squared, r cubed. Numerically, omega cr is about 10, because you wanted this to be compared with the low-lying frequencies. And so this is numerically about 1 part 10 to the minus 14. So this is completely negligible currently, though it may not be negligible in the future. And that's what, so people don't have to worry about this yet. Though I will note that it scales with mass to the positive power, because omega c is proportional to 1 over m. And so for ion traps, where there's a much more massive thing going in a circle, in that case, it is a very strong effect, and is already accounted for at the percent level by ion trap experiments. So this is the easy one, but there's another effect which is actually a lot harder to deal with, which is the transverse effect. So this is the one where you excite the cavity mode and it reflects back onto you. Again, you can guess how big it is by calculating the force from the radiated field coming back to you divided by the force that we already had. So the force we already have is mass times acceleration. The force from the radiated field is charge squared times acceleration over r. That's the typical form of a radiation field. And also I put this q here because if you happen to be near a cavity mode, then radiation amplitudes are enhanced by q. And so this means, and so if you're unlucky, then this can be a much bigger effect. When you plug in the numbers here, now numerically, again, the orbit properties cancel out. You get q alpha over mr, and that's at 10 to the minus 12 times the possible q enhancements. And so that means that at the current level of precision, you need to understand this effect at 1 part in 10 to the 10. And even in the past, if you were near a resonant mode, you had to understand this even back in the 1980s. Yes?
What's the Q again?
Q?
Big Q. Yeah.
Q is the quality factor of the cavity mode that you're ringing up. So it has all these cavity modes have finite damping, and then the quality factor is just like as usual in like E&M and mechanics. So typically, numerically, it's about 1,000 for these cavities. So this can be a big enhancement. So even off resonance, this is important, and even on resonance is extremely important. So we must understand this effect. So how do we calculate it? Well, there's two conceptually different ways of doing it. One is we use classical mechanics. And so what we do is we imagine there's a little charge going in a little circle. We calculate the radiation field of it, account for how it reflects off the boundary, and then figure out how much field there is right back at the charge zone location. And so this, technically, will give you an answer at infinity. Because the field of a charge at its own location is famously infinite, as point charges are very singular. So you need to find some way to carefully remove that part, and then only account for the part that got reflected, which can be done. But in quantum language, the way this comes about is completely different. So in quantum language, it comes about because it comes about from the self-energy diagram at one loop. Because at that order, the diagram consists of the electron emitting a photon and then reabsorbing, which is exactly what's happening here. And specifically what we care about is the difference of this happening when the photon's in the in-cavity propagator, or versus what it is in free space. That gives you the additional shift due to the cavity being there. And so it is a one-loop diagram, but it involves all sorts of things that break the usual symmetries of one-loop diagrams, because the electron is in the magnetic field, so it doesn't have the usual propagator, and the photon is the in-cavity photon propagator, which involves, again, breaks every symmetry, involves a lot of Bessel functions and stuff like that. Now, the classical way of calculating was done for the plates, for simple cases involving a parallel plate, a plate, two parallel plates, a spherical cavity, a cylindrical cavity in the 1980s. And these are hard calculations. These are some really, really majestic tricks Bessel functions are done to calculate this. And it turns out that if you do it classically, you get the same thing as the quantum result for plates. However, to go even further, to get to realistic cavity shapes, it is not really clear how to continue because all of these require subtractive of the Riemann self field, and that requires some really deep tricks which only seem to work in these very symmetric cases. Now on the quantum side, what happens? Well, in the 1980s, a lot of people wrote papers about trying to calculate this in quantum field theory, and there are roughly almost 10 papers that all got different answers. For the simple case of one plate or two plates, which is honestly not much harder than just being in free space. And the reason is because there's all kinds of subtleties that come up because every symmetry you're used to is broken. In this problem, it's very easy to make mistakes, calculate gauge-dependent quantities, calculate things that break symmetries unnecessarily, and so on. And so in the 1980s, many papers disagreed, and by 1990, people finally started agreeing on the correct answer for one plate. And in that case, that's the thing that matches the classical answer for one plate. And so ever since then, people said, well, okay, that was hard enough, so we're going to stop here. Let's just hope that classical mechanics works for the actual non-trivial case of a closed cavity, which has much different modes than these free space with the plate emits, because it just seems way too hard to deal with. And the matter was left at that for 30, 40 years, until the people doing the electron g-2 experiment got in touch with some of us and said, this is actually crazy that this has never been resolved, and now that this effect is becoming more and more important in the subsequent measurements, we're getting extremely worried that maybe there's something wrong here. So, theorists, please help us out, figure out what is going on. So that's what we did. So let's start over and figure out how to set up this diagram. So we need to calculate a self-energy diagram because that affects the energy of the energy levels. And but to say this in a bit more precision, what we really calculate is, of course, the amplitude for the electron that propagates. And the reason that gives you the right answer is because this amplitude has poles at the electron energy levels. And so that means that you can extract what those energy levels are from seeing how these poles are shifted by these loop diagrams. In fact, you can actually also calculate g-2 in this way. So in the textbooks, we always calculate g minus 2 by considering the vertex diagram, because we say it's a property of the electron's electromagnetic field. We just look at how it affects the vertex of the electron. But in principle, you can also calculate it this way. You would say, well, the electron, I calculate the one-loop self-energy diagram in a B field, and I calculate the part of it that depends on the spin states. And this will give you the exact same answer as the usual g minus 2, but it's a lot harder because you have to account for the B field, and that breaks Lorentz symmetry. So that's why we usually do it the textbook way. However, in this case, we also have a cavity, so there's no choice. We have to break Lorentz symmetry in a horrible way, so we got to face these calculations. So here's how you would set it up, and I'm just showing you the equations for decoration. I'm not going to go into all the details of this. The energy level shift depends on this diagram sandwiched between two external electron states. Then this diagram consists of various gamma vertex factors, the propagator of the electron, which needs to be the exact propagator in the external B field, and the photon propagator. Now, I also want to comment, it's really important to use the exact propagator in the B field, because that is the only way you actually get cyclotron motion in the first place. So it's, in no sense is this a perturbative correction. The B field is having a very strong effect on the electron's motion. And then the photon propagator is the thing that is different when you're in a cavity. So if you approximate the electron as being localized at a point, then even so, you still have a sum over all these cavity modes, US and USI, and which depends on both their mode profiles and their mode frequencies. So this is a very, very tremendously ugly loop diagram. And it turns out that, of course, this loop diagram is infinite, as you probably expect. It's log divergence. When you subtract off you need, of course, subtract off the value it would have in free space to get the shift due to the cavity. It turns out then it's actually still infinite, but then you need to subtract off again what you would get if there was no magnetic field, because that also gives you, that also is divergent. And once you do all these subtractions, you get a finite result, and that's the shift in the energy level you want. So here's how we do the calculation. It turns out that if you take the non-relativistic limit of the previous expression, which is quite a delicate operation, involves many, many terms cancel each other out, it turns out that you just recover what you would get exactly in non-relativistic quantum mechanics. And so for the rest of this talk, I'm going to dump all the relativistic stuff and focus on non-relativistic limits, which is already hard enough. So the answer is this plus very small corrections. And this is, you may recognize, as what you would get from second-order perturbation theory in just ordinary quantum mechanics. But of course, the divergence is still there. So this sum right here over the cavity modes is linearly divergent, and you need to subtract it off against what you get in free space, which is the delicate operation of renormalization. Now, you might say, well, why did I even bother telling you about the relativistic calculation if it's very clear that this is non-relativistic because, you know, the electron is non-relativistic? Like, why do we even need to consider relativistic QED? Well, it was not actually completely obvious, because the most famous example of renormalization was actually started in the 1940s with the Lamb shift. And what was found with the Lamb shift, which is a shift energy levels in atoms, is that even though the electron is non-relativistic in this case, the Lamb shift in the non-relativistic theory is still log divergence. So log divergence is not very bad. You can use it to get a decent estimate of the Lamb shift, which is exactly what was done. But to get it quantitatively correct, you had to match it to relativistic QED. And that's exactly what set off the whole renormalization program in the 1950s. So numerically, it shifts the value by a few percent to match it to the UV, but it matters. But in this case, it turns out that there is no natural UV you need. It all is really completely in the infrared. It is finite already when you do the right subtraction in the infrared without having to deal with the relativistic stuff. So now we need to do the subtraction, and this is now the part where the talk gets a bit technical. So I'm going to only outline, I'm going to give you pictures of equations instead of the real equations, but yes?
Can I ask, I mean, in hindsight, I mean, the way we would, say what the relation between quantum mechanics and quantum field theory is that, particle creation is not important, right? So I can somehow project onto the one particle sector, and that's exactly what gives me quantum mechanics, right? Mm-hmm. And, so there should be, even in taking into account, loop effects, there should be a sensible way of doing that. So what I'm asking is there a way in which this result is kind of obvious?
So that's one of those things that's like kind of like the rabbit and the duck optical illusion. So like when I first came into this project, it was obvious to me you didn't need a relativistic. And then I talked to people working that set, and they said, no, it's not obvious at all. And then we flipped back and forth a couple times. I'm currently of the opinion that it was obvious, but maybe next week I'll think it wasn't obvious. And so one reason for that is that in the Lamb shift, it really is not obvious. So there's part of the Lamb shift is due to these vacuum polarization diagrams involving an electron and positron pair popping out. That's a few percent. So that, of course, that involves number changing. But also there's part of the lamp shift just from the self-energy diagram, which does not involve any like virtual positrons or anything. But even that part needed to account for the relativistic theory to get it right.
I mean, you said here the magic word matching, right? And
Yes.
so the thing is that somehow, I mean, people use non-relativistic QED, which is precisely for bound state problems where they do this kind of matching, also in QCD for like charmonium and so on.
Mm-hmm.
So there is a technology that claims that is supposed to match, you know, to quantum mechanics and is supposed to get all the effects, you know,
Yeah.
it's not just a guess that it's quantum mechanics, right?
Right.
And so I would think there's a systematic way of using those things.
Oh,
here.
I mean, there is a systematic, like what started with the lamp shift has now become a systematic method.
Sure.
But the question is whether you need to do any matching at all. And in this case, it turns out it's even simpler. There is no need for any
it's
matching.
kind of a non-renormalization theorem. It sort of
Yes.
says that all the loops don't even renormalize anything. The naive quantum mechanics result is the right one.
Yes, it's because, I'll show in later that basically, it's because this is a very, very deep infrared effect. It really cannot know anything happening at higher energy scales. But it was not a foregone conclusion that this was a purely infrared effect. Because while the lamp shift is log divergent, so it still retains some sensitivity to very high energies.
Yeah.
But this one turns out, when you subtract it off, it becomes completely convergent. So that's a fortuitous thing that happens. I'll show you now how this subtraction works. Now, unfortunately, we're going to have to use some Bessel functions because there's just no way around it. The cavity modes involve Bessel functions. So I'm going to give you the simple example of a spherical cavity radius A, because that's much easier than the realistic shape of a cylinder, but it demonstrates the same points. So when you calculate the energy level shifts, you need to sum over all the modes. And what you end up getting is, it turns out only the TM11P modes counts, and you get an infinite sum of these, but the sum is linearly divergent. And it depends on these things. These CPs are actually Bessel roots, I'll explain later, and there's Bessel functions and stuff like that. But you need to subtract it off against the free space result, which is that in here, the photon states are plane waves. You integrate over all the plane waves. If I do the angular integral to get spherical symmetry, then what's left over is the residual integral over the frequency, and this frequency, the residual integral looks like this. And so I need to subtract off this sum of this integral in a well-defined way. And all these C's are because they're changing to dimensionless variables. So the CP on the sum side is just the mode frequency times A. Z is the cyclotron frequency times A. C is the plane wave frequency times A. So now what we can do is we can regulate the sum of the integral in some smooth way. And because the frequencies only depend on these C variables, whatever this regulator is, it better treat CP and C in the same way. But I want to go further and actually show how to do this subtraction analytically. And if you begin by putting in some random regulator in here, you'll see that these sums are completely intractable. It's just even without the regulator, it's very hard to say anything to simplify this sum. But in fact, I'll show you that for any regulator, this sum and this integral can be subtracted completely analytically using this trick. So here's the trick. So we need to subtract out these two things. So the first trick is, in order to make the sum more like this integral, I need to make sure that the sum makes sense even when p is not an integer. Because here c is continuous, while these discrete mode frequencies are, well, discrete. And that seems very unlikely because Cp is itself a root of a Bessel function, at least of a spherical Bessel function. So it's defined by being the pth root of this expression. And that is, manifestly something that only makes sense when p is an integer. However, there's a trick which was invented about 60, 70 years ago, which is basically just evaluate this thing and then take an arctan. And then this condition is equivalent to c plus arctan c over c squared minus 1 equals pi p. But now what's different about it is that now, because arctan is just a perfectly analytic function, you can regard this as an analytic relation between c and p. And so now I can define the pth Bessel root even when p is not an integer. It's a smooth interpolation. And then if I then plug this back into this expression and apply many, many Bessel identities, I eventually find that this whole summand simplifies to 1/2 c squared minus c squared times dc dp. So it's almost the exact same thing as the integrand, just a bit distorted by this Jacobian factor. So this is just, it doesn't always work out that nicely, but it's just because the sphere is really nice. Now, I need to still find a way to subtract these things, where this is like some kind of distorted, discrete approximation of the integral. And so the second trick is, I'm going to define a contour integral, which can be related to both the sum and the integral, both regulated in the same way. But this approach will let me do it without actually saying what the regulator is. And then finally, the difference between them can be found by comparing the two expressions of the contour integral, and it'll give me an answer that is completely regulator independent. So this is a bit maybe opaque, so I'll show you how this actually works now. So here's what we do. We consider this contour integral of the summand integrate against e to the minus 2ip over minus 1, integrated along this curve. And the reason that I consider this contour integral is because it's engineered to have a pole at every integer p. And now what I can do is, there's some regulator here which I'm not even specifying what it is, but it should cause these, the integrand to get smaller at infinity. And so what that means is I can close the contour at infinity without worrying about picking up a contribution. And then the answer is that it is going to have contributions from the residues of all these poles. And they're precisely F1, F2, F3, and so on, plus the one from this extra pole over here that just was carried along for the ride, the expression for P has a pole in it, F has a pole in it. Now, on the other hand, I can change variables from P to C because there's an analytic relation between them. So if I map everything back to C, I get this equivalent contour integral, where now everything's in the C space, and the contour is a bit tilted. And now this contour integral is the integral of 1/2 c squared over c squared minus c squared. The Jacobian cancels, and then g of c, which is this denominator factor, ends up having a more complicated expression. And now I can evaluate this integral in a different way. What I do is I push the whole contour to the left, so it goes up the imaginary axis. And to do this, I need to go through pick up half the residue at c equals 0. And once you're at the imaginary axis in C space, it is actually very simple. And the reason is because this function that's left over actually has a symmetry property. The values in the top and the bottom are actually opposite of each other, it's up to this plus 1. So then finally, I pull out the plus 1 factor from the bottom parts, I rotate that contour so it goes along the real axis, and I get back the integral that I'm trying to evaluate. With the same regulator there has been coming along for the ride the entire time, plus, of course, the contribution of the pole at c equals 0, and everything else cancels. And so now when I compare these two expressions for A, I get an expression with the difference of the integral and the sum, which are both regulated in the same way, because the regulator was just transferred from P to C space all the way through, that is completely independent of what the regulator was. It just depends on these contributions of the poles at c equals 0 and c equals p, c equals z. And these residues happen to be this. Now, it turns out this is exactly the same as you get from the classical Green's function. So in this case, the classical answer works perfectly. It really is the exactly correct matches the quantum result. Now, the real cavity is cylindrical. So there's a bunch of complications. So I'm not even going to show any equations here. I'm just going to tell you what the complications are. So the first thing is there's actually both T and T modes matter. There's two infinite double sums that have to show up because they both contribute. You can perform one of the sums exactly, but the other one has to be regulated. And then also it depends on the aspect ratio of the cylinder L over A, so you need to separate that part out. You need to subtract against the integral plane waves. There's cylindrical coordinates. There's a bunch of special functions involved. And then finally, we need to relate the sum index n to the continuous C by defining using these tricks again, where I make a continuum in a lot of different decimal roots. And then finally, all these things involve a lot of square roots. And so that means that there's a lot of branch cuts in the argument. So these are a bunch of computations happen, but the strategy is still the same. The strategy is we consider some contour integral, which defines that when you close the contour to the right, you pick up the sum. And then we can change the variable to C. We move the contour to the left to be symmetric. It goes around a branch cut this time. You can actually, there's still a symmetry relation, but now it's the same sign instead of the opposite sign. So what I can do is I can fold the contour up to get only the top parts. And then I take the contour that's there, I make it so it goes straight up instead of to the left and up. And in the end, what I get is that, and I peel off the plus 1 and so on. In the end, what I get is this contour integral is the integral I want plus this remainder integral, which is along this CU contour. But fortunately, this is exponentially damped. And so that means it's easy to evaluate, it's perfectly convergent.
Sorry, because I should have asked before, but I kind of lost. What is all this contour stuff buying you? Like, is it somehow that you're able to write that you're directly getting the difference of the sum and the integral, or what? What is all this contour stuff buying you?
Yeah,
Sorry.
So basically, we don't want to actually evaluate the sum of the integral for a regulator because it depends on what the regulator is. But we start with a contour integral that is engineered to be the sum. But then by changing variables to the integral variable, C, which is where the integral is phrased, I can extract off a part of the contour integral, which is exactly the integral that I want to subtract the sum with.
Oh, okay.
And because it's like it was done by changing variables from the original sum, the regulator is automatically the correct regulator. It's the one that regulates them in the analogous way. So in that way, I can calculate the regulated difference without ever even saying what regular is. And that saves me a lot of headaches, basically. That's what it buys you. This kind of trick, by the way, I mean, of course, this is not in any of the quantum field theory textbooks, but people that do Casimir effect calculations, they often have to deal with, things that are equivalent to loops with, not many symmetries. And so there are similar tricks used in the Casimir world. Same thing with cylinder. Here's the answer to the cylinder. Of course, this is just to show you what kind of thing comes out. In the quantum answer, it's some remainder integral, which is exponentially damped. So that means it depends only on the low frequencies. It's very easy to evaluate. And then a remainder sum involving all these extra poles. And there's actually a bunch more terms for the TM I'm not showing. And then the existing classical result was done by finding the exact Green's function for a cylinder, which is extraordinarily hard. So this is like it's much harder vessel manipulation than what we did. And it gives you this completely different answer, which doesn't really have much resemblance to what we have. Now, it turns out we can show that these are actually analytically the same in certain regimes. Though I'm going to spare you the details of that. And numerically, you can also evaluate what it is, and it is really just exactly the same thing. So here's the cavity shift in units of alpha over MA, like the generic value of it. And here it is in terms of the frequency of the sixth term frequency. And so in both cases, it's some order one thing, except it goes up whenever you're near resonance. And they really are exactly the same. Like, you cannot distinguish any difference at all. And so this means, amazingly, classical mechanics, it really works incredibly well to calculate these things. But now you might be wondering, okay, well, now that we've shown that classical mechanics had the right answer all along, what was the point of even doing any of this? Actually, now that we have the quantum answer, which is phrased in terms of modes, it actually is a lot easier to do precision things with this. Because the classical calculation was extremely delicate. It required you to really know the exact Green's function, like analytically, and then because otherwise you can't subtract off the self-energy part, the self-field part. And but for the quantum answer, it's just in terms of these modes. And in the real cavity, which has modes in different places, you can just evaluate specific cutoffs and calculate the answer. So here's an example with specific cutoffs. If I take the sphere, which is difference of sum and integral, and I just do a hard cutoff on both the sum and the integral, then I can get the right answer. But I need to make sure to put the hard cutoff in the right place. And so you might have seen, for example, that famous question. It's like what's the value of 1 minus 1 plus 1 minus 1 plus 1 minus 1? Of course, it is a half because it's halfway in between. And the reason is because the smooth difference of that versus an integral would be asymptotically 1/2. And the same thing happens here. If you calculate the difference of the sum and integral with hard cutoffs, if you put the cutoff for the integral halfway between the c's of the top c in the sum, then you get the right answer, which is by the same logic. Like, that's just how a smooth regulator should work. But the incredible thing is that the answer is actually not only correct by putting it halfway between, but it's actually extremely accurate even when you have a very small number of terms. So even with just 10 terms in the sum, which is very easy to measure in practice, you can get this cavity shift down to 10 minus 15. And the underlying reason that it's so insensitive to the higher modes is because when we did all this annoying analytic work, what we would always get is terms involving poles at low frequencies, which are accounted for exactly because they're low frequencies, plus a remainder integral involving going up high frequencies, which is exponentially damped, which means that really all the dependence on high frequency information is exponentially suppressed, which means that, well, you can throw away a lot of it and get a really good answer. Yes?
What's the dotted line here?
That's the exact results.
So that's the exact result, and then the blue line is what you do by going halfway in between.
The simplest possible hard cutoff.
I see. Yeah. Okay.
Of course, if you did the wrong hard cutoff, you'd be off by order 1, which would not agree with experiments. So this is already, you gotta be smart about doing the hard cutoff. Now you could also say this is kind of obvious, right? Like, didn't we already know where to put it halfway in between? But for the cylinder, it's actually even trickier because the integral actually involves different parts. It's like it's got 3 terms in it, and different parts of the integral have to be cut off in different ways because they correspond to the thing that matches to a different part, either the TE sum and the TM sum. And TE and TM have asymptotically different frequencies. And so if you just cut off everything according to TE mode frequencies, you get the wrong answer. TM, you also get the wrong answer. But if you separate the integral into the parts and then cut off each one in the right place with 1/2, from the previous slide, then what you get is an extremely accurate answer with just 10 things in the sum, up to 10 minus 15. And so this is great because right now, the experimentalists are worrying about things involving at the 10 to the minus 12, 10 to the minus 13 level, and doing these ad hoc methods to kind of guesstimate what it is. But this really shows that if you measure just a small number of modes, you can get extremely accurate, far beyond what they need in the near future. So that's what we hope to do in future collaborations with experimentalists, is we can treat the real cavity. because the real cavity is actually not an ideal cylinder. You can actually measure the mode frequencies in the cavity, and that's where they painstakingly did. They measured dozens of mode frequencies, and they're all slightly above or below what you would expect from an ideal cylinder. I mean, they're pretty close, but they're maybe 2% higher, 2% lower. And that's because the cylinder is not actually a perfect cylinder. The walls are not perfectly uniform. There's higher connectivity and lower connectivity in different parts. There's electrodes inside that make the electrostatic field. Those perturb the shape. All kinds of these non-ideal effects. But our way of doing it with cellular modes doesn't really care if you have an exact cylinder or not. And so in that sense, I think that in our future work we'll be able to basically nail down exactly how much systematic shift you get from this and quantify the uncertainty quite well. But wait, there's more. So now this entire talk has been about the standard model. Everyone loves standard model, most precise thing in the world, et cetera, but you might be wondering, what's the BSM angle? Could this tell something about beyond the standard model, besides the fact that this is a good thing? And I think that the way of thinking here, that reveals that classical and quantum actually agree, even though they look very, very different, actually tells you something useful about how to analyze BSM physics. So I'm going to give you some examples now. So here's an example. Let's suppose we have ultralight dark matter, such as axions. I know it's a really big change of subject. For some people, axions are practically already in the standard model, but for us, let's just I'm introducing a new topic here. So let's suppose that we had some kind of coupling to external axions. One could consider what would happen to the force mediated by axions if you also couple to external axions at the same time. And so what has been popular recently is that people realize that you can calculate this effect in a simple way by saying, I can calculate it formally as a loop diagram, where the loop diagram propagator is modified by there being a background. So basically, this propagator over here has a delta function in it, so when you evaluate this diagram, it's really exactly the same as this diagram. So it's a trick to make this kind of complicated tree-level diagram be like a loop diagram. I mean, it's not really a trick. It's like the main method of thermal field theory. That's like the main idea of what they do. And so then when people calculated it, they found a lot of surprising results. For example, this year people found that the force mediated by one axion is 1 over r cubed in the dipole-dipole force. But if you have this effect in there and modify one of the propagators, you get a sum over 5 of these formal loop diagrams, and you get a force that's 1 over r and spin independent, which is very weird because the axion is most definitely not coupled like in that kind of way. And people have claimed maybe this is some inherent feature of quantum mechanics that is just too deep to ever understand from the classical side. And what I realized is that actually it's not actually quantum at all. If you calculate everything classically very carefully, it turns out that even in the classical equations of motion, there's a subtle monopole parts of the sourcing, basically, that gives you the exact same answer. It's qualitatively exactly the same as doing these 5 loop diagrams, but it only needs 3 lines. And more generally, that if you were dealing with ultralight dark matter, because it's so low frequency and so weakly coupled, a classical analog for it should almost always exist. Now,
this is the same thing as these, like Ken Van Tilburg called these wake forces.
This is
we
example
also
wake force.
found for our, if you have a quadratic coupling, right, you always get these.
That's right,
Yeah.
yes. He focused in the case of quadratic couplings. This also happens for linear couplings at higher
Yeah.
order. So this is the analog of that at higher order.
Right.
I haven't bothered writing this up, but this is just a thing that happens.
Yeah.
And it's actually quite interesting. So basically, it's like the coupling to the axion field has a term that depends on the acceleration of the particle, which usually drops in the classical limit, but it is there. So now people have also argued, for example, that if you take the g-2 shift, we all know that there's, the axion can change g-2. It's in this loop diagram, and the change is very, very small. So it's completely negligible. But some people claim that if you put in the propagator involving the background modification, then you get a much, much larger g-2 shift proportional to the density of dark matter. And so there's a long series of papers, including one in PRL, that claim that by doing this, we actually have already probed the axion many orders of magnitude stronger than by any other method. But this also turns out to be very misleading. So first, there's a claim that we didn't see this before because this is a loop diagram, it's some very deep quantum thing, it cannot be understood classically. And what I showed earlier in this year is that it turns out, again, it actually is completely classical. So what you need to do is you need to write down just the equations of motion for just an electron. So the Lorentz force law plus the Bargmann-Michel-Telegdi equation, so the spin precession equation with relativistic corrections. And it turns out that all these effects are actually already there in the classical equations of motion, these two, but you need to account for the relativistic corrections, and you need to work the second order in the axion, because there's 2 of these vertices, and then you need to make sure that you carefully retain terms that do not average to 0. So almost everything averages to 0, there's a few things that don't, and they're in the relativistic corrections, and when you get all this stuff out, you'll get the same formal result. Which is a bit of a tricky calculation, because This is kind of like calculating gravitational wave memory or the quantum motive force. These are all classical effects, but they are a bit tricky to extract. But when you do it, you get the same thing. But it also shows something else, which is that this only works if the particle is free. And this is one of those things that is actually very subtle about Feynman diagrams and the way that we calculate things usually in textbooks. Almost always when you calculate Feynman diagrams, get g minus 2, EDM, whatever, we assume that the particles are free. We project against an external plane wave. And that's actually, for virtual particles, that's a very good approximation, because the effect is fundamentally due to very high energy virtual particles that are going all the way up to the UV cutoff theory, while the binding, say in an atom, is only at EV scales. However, when you calculate things involving the analogs of these things with ultralight dark matter, the oscillation frequency of ultralight dark matter might be something like micro EV or maybe nano EV. And in that regime, you absolutely cannot neglect the binding. Actually, the binding actually dominates over the effect, and it turns out to average out these things. But this is invisible in the standard way of calculating with the textbook method, because that's optimized for these high-frequency virtual particles. But in terms of the classical thing, it's very easy to see. Basically, like, if you're locked in place, then the force wiggling back and forth can't do that much.
Sorry, what is the IR cutoff physically? What's the physical effect that's giving the IR cutoff?
It depends on the way that the g minus 2 is measured. So sometimes it's measured, for example, in these electron g minus 2 experiments, the electron is already orbiting in the trap, and its orbit frequency is a milli-eV. And so that means, for example, if I try to like move it, I can't accumulate any speed unless I'm wiggling it faster than milli-eV, because otherwise it'll get smeared out by over the orbits. And so if the dark matter mass is below milli-eV, then this effect does not hold. At least this equation doesn't work. But this equation, gets stronger lower dark matter mass. So all the strong sensitivity goes away. Now, if it's the muon g minus 2 experiment, it is a free particle, but it is going in a big circle, and the orbit frequency is something like I think nano eV. So you still have an infrared cutoff. And if it's an atomic spectroscopy thing, then it's the binding energy of the atoms.
Okay, it's basically the electron motion.
Yes,
one
that's
from
right.
form to it.
That's right.
Yeah.
It's very easy to see when you go through the classical thing that this prevents any of these effects from building up. But in the quantum way of calculating it, unless you have to project it onto these the proper external states, which is very, very complicated, and so no one does it. So that it makes it look like these things don't have cutoffs, but they do. Now, so the conclusion is, it turns out, and this is always a fun thing to find, physics works better than we expect. So the relativistic quantum electrodynamics, inside such a simple theory, actually it already knows about all these very subtle long-distance phenomena. What I've shown in this talk is that the difference in these two diagrams is indeed what you get in this classical analysis. And in general, classical physics works better than many people might think, especially in the far infrared. On the other hand, derivations that use quantum language can also have their own benefits, because in this case it gives rise to this expression using mode sums, which is easier to generalize to a realistic cavity. And so from the lamp shift to the cavity shift, for 75 years, we've been continuously being surprised and delighted by the rich physics of g minus 2, and I hope we will continue to be surprised in the future. Thanks a lot for your attention.
More questions?
So, in this calculation, you found that basically quantum and classical result are the same. Because we are working IR, so we expect there should be no difference to very high precision.
Yeah.
Okay, and do they have a temperature down to 10 to the minus 15 something, or?
Well, in this case, the typical frequency in the trap is milli-eV, so you only need a temperature much below milli-eV.
Is it 10 to the minus 15 below milli-eV?
It's okay because, so the thermal occupancy goes down exponentially when you're at low temperature, so it really is perfectly the ground state. Like, you can cool the micro EV versus milli-eV, that's like e to the minus 1,000, so it's, the thermal corrections are very small in this case.
Even way smaller than minus 15.
Yeah, way, way smaller. Also, they can actually directly measure the state it's in, so like when they say that it's in the ground state, they really can prepare it by like projectively measuring what state it's in, basically.
I'm trying to understand the classical versus quantum. So the loops that you calculated, they have an h bar.
Yeah,
so
so
I would say the
evidently,
quantum.
somewhere the h bar cancels itself out. But we use natural units too much, right? It's like I couldn't tell you exactly where it cancels itself out.
When you do this, like if you do this stuff, you have to keep track of the fact that, when we say the h bar is out in front of the action, then the mass really has units of 1/length. Momentas are really wave numbers and things like that. So
There's a lot.
yeah, when there are a lot of factors of h bar that you have to use to convert to physical quantities.
But conceptually, you can say what happens is, in the beginning, you have dependence on the electron Compton wavelength, which depends on h bar. But when you do all the subtractions right, all that should cancel out, and the only dependence that's left over is on the physical size of the cavity, which is just some h bar dependent thing. It's, a centimeter or so. So somehow that's how it gets cashed out.
It does make you wonder, though, right? If it might be worth thinking about just to see if, I mean, the fact that you really are getting, it looks like exactly, as far as you know, it's exactly the classical result.
Exactly,
right?
yeah.
And so maybe there's a, better reason for that. And if you think about the scaling with h bar. Like, the people that do these gravity wave things, right? That's exactly what they're doing, is they're writing down these loop diagrams, right? But then they're extracting out, they're taking the h bar goes to zero limit, and they're extracting it out,
Yeah.
right? And they're getting things that you could have gotten from, post-Newtonian type calculations where you're iterating some differential equations, right? So it doesn't look totally dissimilar from what you're doing here.
Yeah.
Except he wants the physical value of h bar, not 0.
Well, he's getting the right answer from a classical calculation, which presumably means that calculation doesn't know about h bar,
Yeah, it doesn't. Yeah.
right?
Well,
And so somehow the quantum, so I'm just saying it is non-trivial, right? You don't just, when they do these things for these gravity waves, right, they're taking precisely some limit where you have to take the system, you have to take some appropriate scaling limit to make it
Yeah.
classical. I don't know if it's really the same thing or not, but there's some big numbers here that are making this classical, right?
Yeah. Yeah.
Like the size of the cavity, presumably, and things like that.
Yeah.
But here it's in the ground state, right? We're looking at the electron in the lowest energy level.
Yeah, but somehow this is a
Least
perturbative correction, right? You're not like, the classical thing doesn't know about the ground state wave function either, but it's somehow calculating
Yeah.
the right thing.
And that's
right?
a fortunate thing. Basically, it's like essentially harmonic, so you don't even need to know how wide the orbit is, basically. It cancels out in the classical calculation. Which, I mean, that was also like a lucky break. Like, if there was some non-harmonicity, I think it wouldn't match perfectly. So it is, I think, a bit subtle. I'm not really completely sure where the h bar, at what point it goes away.
I mean, g-2 is dimensionless. And you said it's going to be classical because it depends on the cavity size,
Yeah.
but it must depend on something else so that you can get a dimensionless answer.
Well, like parametrically, it always ends up being something with a prefactor of alpha over ma in natural units. So, I mean, alpha has an h bar in it, right? And m also has an h bar for the Compton wavelength. So,
Well, physically, like you described in the beginning, it's a ratio of frequencies.
yeah,
So somehow, in that sense, it is truly a dimensionless quantity, right?
yeah,
It's just a ratio of frequencies.
right. I mean, even like in the normal one loop correction is alpha over 2 pi. There's no, I mean, I guess alpha has an h bar in it if you count that. So it's,
Yes, I do.
I mean, yeah. But in this case, it's alpha over m that the h bars cancel out implicitly, I think. Yeah.
So this quantum result and then this classical result, you said that you can show analytically they're the same in certain limits,
Yes.
but you can't, and then you plug it into a computer and show that you get exactly the same answer.
Well, I
numerically,
would
or-
say I can't. I
Have you
honestly haven't
discovered
tried
a new
that.
Bessel
Okay.
function identity?
Yeah, right.
I don't want to. The simple case is when the length goes to infinity, then it's actually pretty easy. A lot of terms go away, but I just don't even want to think about them.
Yeah, I mean
it's basically like the reason it's complicated is because there's an infinite number of ways to orient the remainder contour, so you get an infinite number of answers. It turns out the one that gets close to the classical answer involves putting the contour in an L shape that goes left and then straight up. But then that part also goes through some poles, which makes it hard to numerically evaluate. It's like kind of a pathology of the classical answer, but that form makes it easy to match, but not in all cases. I mean, it's one of those annoying problems, so that's why I settled for numeric pairs in the end.
Yeah. Okay.
Mm-hmm.
Could you get the quantum correction by calculating two loops?
I honestly, yeah, I don't know. That's really interesting. I mean, so like parametrically, you would assume the 2 loop is 10 to 3 down from the 1 loop, so it contributes at 10 to the minus 14 plus times maybe. So no one has ever considered this, even for the plate case. So what my guess is if you put in the 2 loop correction, basically part of it should factorize to a part that's high energy and part that's low energy. So the low energy parts involves, all the cavity properties, while the high energy part might be, that at 1 loop maybe the G is shifted, so then the particle has more magnetic moment than you would expect. And so then it could, if that was true and you could factorize it that way, it would just be a multiplicative correction on the 1 loop result, which is classical. But I mean, if it doesn't work that way, then I don't know. Yeah, I don't think anyone's ever thought about it. I'm not completely sure. But it does seem more plausible that you get something that's inherently non-classical because basically, like in the 1 loop, you can think this isn't really some sort of virtual photon or anything. It really is just like the real photon you're emitting and then immediately reabsorbing in some sense. But with a 2 loop, you have really more virtual stuff in the middle.
Okay, let's thank Kevin again.
Thanks, everyone.